Good evening. M.C. Escher was one of the greatest artists of the 21st century. But why is this? Who was the man behind the artwork? Join me as I take a journey through Escher's life and work and see just why his artwork influenced so many people. Next on Artist Tonight. Born in Leeuwarden, Netherlands, when Escher was 5 years old, he moved to Arnhem in the Netherlands as well. After failing his high school exams, he quickly enrolled into architectural school. But after only a week, he decided to pursue graphic design. For the next 11 years, Escher traveled throughout Italy, practicing his artwork and drawing sketches. Here, he also met his wife, Jetta Umiker, and they also had their first child here in Italy. Finding the Italian political culture not to his liking, M.C. Escher moved to Switzerland in 1935. But soon thereafter, he and his family moved to the Mediterranean again. It was here where Escher began to get the ideas for his most famous works, such as tessellations and advanced mathematics. After World War II, Escher moved back to Holland, now free to continue his work in art and mathematics. It was at this point where his work began gaining fame and notability. Throughout the latter years of his life, Escher spent his time drawing and giving lectures at colleges and universities. He died in Loren, Holland in 1972. We now know that M.C. Escher's life was one filled of travel, mathematics, and art. But why are his paintings so popular? Why do we still study them to this day? Is there anything more than just a bunch of incoherent lines on a page? The answer, my friends, is yes. That answer also lies in a type of non-Euclidean geometry called hyperbolic geometry. Let's take a closer look. In order to better understand how M.C. Escher used non-Euclidean geometry and hyperbolic geometry in his drawings and sketches, we need to first take a look at Euclidean geometry and Euclid's postulates. Now, in ancient Greece, Euclid, a famous mathematician, came up with 5 postulates which today determine the base of Euclidean geometry. They include rules about lines and points and circles. And the first 4 postulates have all been proved and, for the majority of the time, remain constant. But Euclid's 5th postulate, that's a different story. Euclid said that for every line that exists on a plane, there exists only one other line that will never intersect with it, meaning there exists only one line that is parallel to another line. Now, Euclid was never able to prove this, and in the years since, mathematicians have never proved this either. And this is where we start getting non-Euclidean types of geometry, such as hyperbolic geometry. Hyperbolic geometry says that there is an infinite number of lines that are not parallel to another line. So, on a hyperbolic plane, this would be translated to this. Now, it's a little hard to understand in 2D, so I'll show you how this translates to 3D and then how it translates to M.C. Escher's drawings and sketches. Now, hyperbolic space can be quite difficult to understand if you're just looking at it 2D. So I brought in this wooden bowl to help demonstrate what I'm trying to get at here. So notice how all the lines, they're not straight even though they are parallel here. Now the reason they're not straight is because the 3D surface itself expands at the top and is narrow at the bottom, so it distorts the lines. So that is why Euclidean geometry doesn't really work on a 3D surface like this, because Euclid's fifth postulate especially just doesn't translate from a 2D plane like this to a 3D plane like this. So that is how M.C. Escher drew his sketches and his drawings, by using the hyperbolic plane as a means of distorting the shapes and the angles and the distances between what he was drawing on the page to make it look 2D, but when you're looking at it, something about it seems a little off, and that's because it's drawn by using hyperbolic space, not Euclidean space, which is made up of those 5 postulates. Now you may be wondering, what does hyperbolic geometry have to do with M.C. Escher and his sketches and drawings? Well, we can see here in this sketch of what looks to be some fish or some birds, that he is drawing them in hyperbolic space and not Euclidean flat space. It's just this hyperbolic space translated onto a 2D surface. So you can see that by how everything in the middle is larger, and as it gets wider, the tessellations begin to gradually repeat but also get smaller. Now this is because this is drawn as if you're looking up at, say, like a globe or something, and how globes, when translated onto 2D surfaces, they become maps, and oftentimes maps are not accurate when it comes to the edges. So we can see here how the edges are being very distorted, just like a map.